Right now, as you hear these words, 100 trillion particles are piercing through your body. They pass through the chair beneath you, through the floor, through the bedrock and magma of the Earth itself. They are muons born 15 miles above your head when cosmic rays slam into the atmosphere at nearly the speed of light. Most of them pass through you without touching a single atom. Ghosts in the machine of reality, but some of them wobble. They spin like microscopic tops, oscillating to a rhythm that 50 years of physics cannot explain. A rhythm that should not exist. A rhythm that on Christmas Eve 2025 finally forced us to rewrite everything we thought we knew about the universe. This is the story of that rhythm, and the story of the people who refused to stop listening. The date is April 7th, 2001. Brookhaven National Laboratory, Long Island, New York. It is 4:37 in the morning, and Dr. Theodore Blackwell has not slept in 31 hours. He stands alone in the control room of the Muon G2 experiment, staring at a computer screen that displays a graph he has seen 10,000 times before. The predicted wobble of the muon particle. A perfect sine wave calculated to 8 decimal places. The triumph of 20th century physics rendered in green pixels against a black background. Beside it in red is the actual measurement. They do not match. Theodore is 62 years old. He has been hunting particles since before most of his graduate students were born. He has gray hair that refuses to lie flat, reading glasses perpetually perched on his forehead, and a reputation for being the most conservative experimentalist at Brookhaven. The kind of man who checks his calculations 3 times before writing them down. The kind who says, "We need more data," when everyone else is ready to celebrate. But right now, his hands are trembling. The difference between the two curves is microscopic. 8 parts per billion. If you tried to show it on a normal graph, you would not see it. But this is not a normal graph. This is the result of accelerating muons to 99.94% the speed of light, trapping them in a superconducting magnetic ring 50 feet wide, and measuring their spin to a precision that would make a Swiss watchmaker weep. And the muons are precessing wrong. Theodore reaches for the phone, puts it down, reaches for it again. He knows what will happen when he makes this call. The skepticism. The demands for independent verification, the whispered conversations in hallways about instrumental error and statistical flukes. He remembers what happened in 1998 when another team claimed to see neutrinos oscillating in ways the standard model forbade. The ridicule, the career-ending accusations of sloppiness, but he also knows what he is looking at. The dataset contains 4 million muon decays. The statistical uncertainty is 0.000004. The systematic errors have been analyzed, cataloged, eliminated. The magnetic field strength is known to 9 significant figures. The detector calibration has been verified by 3 independent methods. And still the muons exhibit excess magnetic moment. Theodore picks up the phone. "Bill," he says when the line connects. "It is Theo. You need to come to the lab, now." A pause. Static on the line. Then, "Theo, it is 4:30 in the morning." "I know what time it is." "Did something break?" "No," Theodore says. He looks at the screen again. Red curve, green curve, the gap between them like a crack in the foundation of reality. Nothing broke. That is the problem. To understand why a wobbling particle matters, you need to understand what the universe is made of. For most of human history, we thought the answer was simple. Earth, air, fire, water. Then atoms. Then protons, neutrons, electrons. Each generation peeled back another layer, convinced they had finally reached the bottom. But the bottom kept moving. By the end of the 20th century, we had arrived at something we called the Standard Model. It was not a simple picture. It contained 17 fundamental particles organized into quarks and leptons and bosons governed by quantum field theory equations that filled textbooks. But it worked. My God, it worked. The Standard Model predicted the existence of particles decades before we built machines powerful enough to see them. It calculated the strength of forces to 10 decimal places and got every digit right. It told us that matter and energy were interchangeable, that empty space was full of fields, that the vacuum itself could boil, with virtual particles popping in and out of existence. And at the heart of it all were four forces. Four fundamental interactions that governed every event in the universe, from the fall of an apple to the birth of galaxies. You know them. You have lived with them your entire life. Gravity is the first. The invisible tether that pulls you toward the Earth, that keeps the moon in orbit, that shapes the slow, majestic dance of spiral galaxies across billions of years. It is the weakest of the four forces by an almost comical margin. Right now, the entire mass of the Earth is pulling down on you with its gravitational field. But when you stand up from your chair, the chemical forces in your muscles overcome the gravity of an entire planet. Weak, yes, but infinite in range and patient. Gravity never stops pulling. Electromagnetism is the second. This is the force of light and lightning, of magnets and radio waves of every color you have ever seen. When you touch a solid object, you are not actually touching it. The electrons in your fingertips repel the electrons in the surface, and you feel that repulsion as solidity. Matter itself is mostly empty space held in shape by electromagnetic fields. This is the force that binds atoms into molecules, that allows chemistry to exist, that makes life possible. Then come the two nuclear forces operating in the hidden realm of the atom's core. The strong nuclear force is the cosmic glue. Inside every atomic nucleus, protons are jammed together, each carrying a positive electrical charge. They should explode apart instantly, repelled by electromagnetic force. But they do not, because the strong force binds them together with a grip so ferocious that breaking it releases the energy of nuclear bombs and the light of stars. It is the most powerful force in nature, but it has a range smaller than a single proton. Step outside that microscopic arena and it cannot touch you. Finally, the weak nuclear force, the quiet architect of transformation. This is the only force that can change the identity of a particle, turning a neutron into a proton, triggering radioactive decay, allowing the nuclear fusion that powers the sun. Without it, the stars would go dark. The universe would freeze. Four forces. Four pillars holding up the temple of reality. And for 50 years, we believed the temple was complete. The Standard Model was tested in particle accelerators across the world. Thousands of experiments, millions of measurements, uncountable verifications. Every prediction confirmed, every calculation vindicated. By the 1990s, some physicists were quietly suggesting that fundamental physics was essentially finished, that we had mapped the basement of reality and found all the rooms. There were still mysteries, yes. Dark matter, dark energy, the unification of quantum mechanics and gravity. But these were problems of application, not foundation. The four forces were settled science. Theodore Blackwell knew this. He had helped build the Standard Model one careful measurement at a time. He had dedicated his career to testing its predictions with ever greater precision, expecting always to find confirmation. What he found instead on that April morning in 2001 was a muon that would not obey. By noon, the control room is full. 12 physicists crowd around monitors, running calculations on laptops, arguing in the shorthand of people who have worked together too long. The air smells like coffee and dry erase markers. Someone has ordered pizza, but the boxes sit unopened on a desk. Theodore stands at the whiteboard, marker in hand, walking through the analysis for the fourth time. The muon G factor, he says, pointing to an equation, should be exactly 2.00233184. He writes the number with careful precision, each digit formed slowly. This is not a guess. This is a calculation that accounts for every known particle in the universe. Every quantum field, every virtual interaction, every loop diagram in the perturbation expansion. It took hundreds of physicists' years to complete. The theoretical uncertainty is smaller than the width of a human hair stretched from here to Los Angeles. He pauses, turns to face the room. We measured 2.002339192. Silence. One of the graduate students raises a hand. Dr. Blackwell. That is only a difference of 0.00000008. Could it be instrumental error? Theodore finishes. We thought so too. We calibrated the magnetic field 16 different ways. We checked for stray fields, temperature gradients, power supply fluctuations. We accounted for the Earth's rotation, the gravitational field variation, the position of the moon. He draws a circle on the board, labels it error budget. Our total systematic uncertainty is 0.000004. The statistical uncertainty with 4 million events is approximately the same. The discrepancy we are seeing is twice the combined uncertainty. Another voice from the back. What is the sigma? Theodore writes on the board. 2.6 sigma. 2.6 sigma, he says quietly. Not enough to claim a discovery, just enough to say something is anomalous. The room erupts. Voices overlap, arguing about muon polarization and detector acceptance and background contamination. Theodore lets them talk. This is how science works. Skepticism first, faith never. But he knows what he saw in those early morning hours. The pattern in the data is too clean, too consistent, too stubborn. This is not noise. This is a signal from something we do not understand. Let me tell you what a muon is. Imagine an electron, that familiar particle, orbiting every atom, carrying electricity through every wire in your home. Now imagine making it 200 times heavier. That is a muon. It is identical to the electron in every other way. Same electrical charge, same quantum spin, same response to all 4 fundamental forces, but heavier, unstable. A muon lives for only 2 microseconds before decaying into lighter particles. They are born constantly in Earth's upper atmosphere, created when cosmic rays from distant supernovae and collapsing stars strike nitrogen and oxygen molecules. They rain down on you at a rate of about 1 per square centimeter per second. Most pass through your body without interacting with a single atom. But in those 2 microseconds of life, they do something remarkable. They spin. Every particle with quantum spin behaves like a tiny magnet with a north pole and a south pole. When you place a muon in a strong magnetic field, it does not simply align with the field like a compass needle. It precesses, oscillates, like a spinning top tilting as it rotates. The rate of that precession is determined by the muon's magnetic moment, a quantity we call the G-factor. In a perfectly empty universe, the G-factor would be exactly 2, but the universe is not empty. It is full of quantum fields that permeate every point in space. And as the muon spins, it constantly interacts with those fields. Virtual particles flicker into existence around it. Photons, W bosons, Z bosons, quarks and antiquarks and gluons appearing from the vacuum for a fraction of a second before vanishing again. Each of these ghostly interactions gives the muon a tiny electromagnetic tug, changing its precession. The Standard Model can calculate these interactions, every single one. The mathematics is horrifying, involving Feynman diagrams with dozens of loops, integrals over infinite momentum ranges, renormalization procedures that would make a sane person weep. But it can be done. And the answer it gives is G equals 2.002338184. Measure anything else, and you have found something the Standard Model does not predict. Something outside the 4 known forces. Something new. The weeks after the announcement are brutal. Theodore presents the results at a conference in Michigan. The reaction is polite skepticism, at best open hostility at worst. A theorist from Princeton stands during the question period and suggests that the Brookhaven team has underestimated their systematic errors. A senior experimentalist from CERN wonders aloud whether the statistical methods are sound. The criticism is not personal. This is how physics works. Extraordinary claims require extraordinary evidence, and 2.6 sigma is not extraordinary. It is merely suggestive, interesting, worth investigating, but not worth rewriting the laws of nature. Theodore returns to Brookhaven and does what he has always done. He checks everything again. The team spends 6 months analyzing data looking for any error they might have missed. They find none. The anomaly persists, but the community moves on. 2.6 sigma is not 5 sigma. The gold standard for discovery. Without that level of certainty, the muon anomaly becomes a footnote, a curiosity, something to remember when planning future experiments, but not something to lose sleep over. Theodore retires in 2006. He is 67 years old. On his last day at Brookhaven, he stands in the control room where he saw the first hint of the anomaly, and he thinks about the wobbling muon. He thinks about it a lot in the years that follow, because he knows what he saw. And he knows with the certainty that comes from 3 decades of careful measurement that the muon is trying to tell us something. The question is what, across the Atlantic beneath the border of France and Switzerland, another machine is preparing to listen. The Large Hadron Collider is the most powerful particle accelerator ever built. It is a ring 17 miles in circumference, buried 500 feet underground, cooled to a temperature colder than outer space. When it activates, 2 beams of protons race around the ring in opposite directions, accelerated to 99.99999% the speed of light. Then they collide. In those collisions, energy becomes matter. For a fraction of a second, the conditions of the early universe are recreated in a space smaller than a proton. Particles that have not existed since the first microsecond after the Big Bang flicker into being live their brief lives and decay into cascades of lighter particles that spray outward like shrapnel. Surrounding the collision points are detectors: ATLAS, CMS, LHCb, ALICE. Each one is a cathedral of steel and silicon and superconducting wire designed to track every particle that emerges from the wreckage. Dr. Dominic Archer has spent 15 years building one of those detectors. He is 68 years old in the year 2014, tall and lean with white hair and the weathered face of a man who has spent too many years underground. He walks with a slight limp, the result of a climbing accident in his 30s. His colleagues call him the Huntsman, partly for his last name, partly for his relentless focus when tracking down anomalies in data. Dominic is not looking for new physics. He is looking for precision. The LHCb detector is designed to study beauty quarks. These are heavy exotic particles that exist for only a trillionth of a second before decaying. They are remnants of the early universe created naturally only in the violence of the Big Bang. In our cold modern cosmos, they appear only when we force protons to collide at energies high enough to tear the fabric of spacetime. Beauty quarks are interesting for many reasons, but the one that matters most to Dominic is this: when they decay, they transform into lighter particles in ways that the Standard Model predicts with exquisite precision. They are nature's test of our understanding. Dominic does not expect them to fail the test. He has been measuring particle decays his entire career, and the Standard Model has never been wrong. Not once, not ever. But he measures anyway. Because precision is its own reward. Because knowing something to 9 decimal places is better than knowing it to 8. Because science is not about faith. It is about checking. And in 2014, when he checks, he finds something strange. The principle is called lepton universality. It states simply that the universe does not care whether a particle is an electron or a muon. They are identical in every way except mass. They carry the same electric charge, respond to the same forces, participate in the same quantum interactions. When a beauty quark decays, it can produce either an electron or a muon. The ratio should be exactly 1 to 1. 50% electrons, 50% muons. A perfectly fair coin flip governed by the impartial laws of quantum mechanics. Dominic's job is to count those decays, billions of proton collisions, trillions of particles, and in that vast ocean of data isolate the rare beauty quark events and measure the electron to muon ratio. He expects to find 1.00. He finds 0.846. At first he assumes it is a mistake. Detector efficiency reconstruction algorithms, background contamination. There are 1,000 ways for a measurement to go wrong. He and his team spend months checking every one. The anomaly does not go away. More data comes in. The ratio stabilizes at 0.84 plus or minus 0.04. The statistical significance climbs. 3 sigma, 3.1 sigma. Beauty quarks are decaying into electrons 15% more often than muons. The universe is showing favoritism. Dominic stands in the control room of LHCb looking at the same graph Theodore Blackwell looked at 14 years earlier. A predicted value, a measured value, a gap between them that should not exist. He thinks about calling Theodore. He has met the older physicist at conferences, shared coffee in hotel lobbies, discussed detector design. He knows about the muon G2 anomaly. Everyone in the field knows about it. But this is different. Beauty quarks have nothing to do with muons precessing in magnetic fields. Different particles, different experiments, different measurement techniques. And yet both anomalies point in the same direction. Both suggest that the universe treats muons differently than electrons. Both whisper that something is pulling on heavy particles in ways the standard model does not account for. Dominic does not believe in coincidences. He publishes the results in 2019. The reaction is similar to what Theodore experienced. Polite interest, cautious skepticism, suggestions for additional systematic checks. The data is good, but 3.1 sigma is not 5 sigma. Not enough to claim a discovery, just enough to raise an eyebrow. But Dominic is patient. He has been building detectors for 40 years. He knows how science works. You do not shout about anomalies. You measure them again and again and again until the data is so overwhelming that even the skeptics have to listen, or until you find the error and the anomaly disappears. He hopes quietly for the former. Because if both he and Theodore are seeing the same thing from different angles, then something fundamental is happening. Something that will require new physics to explain. Something that might be real. The year is 2021. Theodore Blackwell is 82 years old. He lives in a small house outside Chicago near Fermilab, where the muon G2 experiment has been resurrected with upgraded detectors and improved sensitivity. He is officially retired, but he still visits the lab twice a week, shuffling through hallways he has walked for decades, checking in with graduate students who think of him as a relic from a simpler era. They are kind to him. They listen when he talks about the old Brookhaven results. But he can see the doubt in their eyes. 20 years is a long time in physics. 2.6 sigma anomalies have vanished before. Most of them were errors, but this one has not vanished. The new Fermilab results come in April, exactly 20 years after Theodore first saw the anomaly. The statistical precision is better. The systematic errors are smaller. The detector is improved, and the muon is still exhibiting excess magnetic moment. The new measurement G equals 2.00233188. The standard model prediction G equals 2.00233181. The discrepancy, 4.2 sigma. Theodore is in the control room when the results are unblinded. The team has spent months analyzing the data blind to the actual measurement so that no unconscious bias can creep into their methods. When the code finally runs removing the blinding offset, the room falls silent. 4.2 sigma. Not enough for a discovery, but closer. So much closer. One of the graduate students turns to Theodore. Dr. Blackwell, you were right. Theodore shakes his head slowly. We are not right until we are certain, and we are not certain at 4.2 sigma. But his hands are trembling again, just like they did 20 years ago in Brookhaven, because he knows what this means. The anomaly is real. It has survived 2 decades of scrutiny, 2 different experiments, thousands of checks and rechecks. The muon is not obeying the standard model. And if the muon is not obeying, then something else is acting on it, something invisible, something we have been blind to for the entire history of physics. Theodore leaves the control room and walks out into the April afternoon. The sky is clear pale blue, scattered with contrails from jets passing overhead. Somewhere up there, 15 miles above his head, cosmic rays are slamming into the atmosphere. Muons are being born raining down through the sky, through his body, through the earth. Precessing. He thinks about Dominic Archer at CERN measuring beauty quarks with the same obsessive precision. Different continent, different particle, different experiment, same anomaly. Theodore pulls out his phone. His fingers are stiff with age, but he manages to find Dominic's number in his contacts. They have exchanged emails over the years, comparing notes, discussing systematic errors. The call connects. Static. Then, a voice with a faint British accent. Theo. Dominic. Theodore says, I think it is time we talked. They meet 6 weeks later in Geneva. A small cafe near CERN, windows open to the summer air, the Alps visible in the distance. Theodore has not traveled internationally in 5 years, but this is important. This is too important for emails and video calls. Dominic looks older than Theodore remembers. But then, they are all old now. The generation that built the standard model, that measured the 4 forces to impossible precision, that thought they had finished the puzzle. They order coffee. Make small talk about the flight, the weather, mutual colleagues. Then Theodore pulls a laptop from his bag and sets it on the table. Show me your data, he says. Dominic smiles faintly. Straight to business. I like that. He opens his own laptop, pulls up a series of graphs. Beauty quark decays. Measured ratio of electron to muon final states. 0.846 plus or minus 0.039. 3.1 sigma discrepancy from the standard model. Theodore studies the graphs. What is your dominant systematic uncertainty? Trigger efficiency. The muons are harder to reconstruct than the electrons. But we have checked it 17 different ways. The correction factor is solid. 17, Theodore repeats. He understands. He has checked his own measurements more times than he can count. We are at 4.2 sigma now, muon G2, same particle, same bias against muons. Dominic nods slowly. I know. I have been following your results. They sit in silence for a moment, watching tourists walk past the cafe window. Somewhere beneath their feet, 500 feet underground protons are circling the LHC at near light speed. There is more, Dominic says finally. He pulls up another graph. Cosmic ray data. From Pierre Auger Observatory in Argentina. High-energy muons from atmospheric showers. They show the same anomalous behavior, same electron-muon asymmetry. Theodore leans forward. 3 independent sources. 3 independent sources. Different detectors. Different techniques. Different continents. Dominic meets his eyes. Theo, this is not instrumental error. This is real. Theodore takes a slow breath. He has waited 20 years to hear someone say that. Someone whose judgment he trusts. Someone who has checked the data as carefully as he has. If it is real, he says quietly, then the standard model is incomplete. Not incomplete, Dominic corrects. Wrong. At least wrong about something fundamental. And that something is the 5th force, Dominic finishes. Something that interacts with heavy leptons and quarks, but not with light ones. Something that has been invisible to us because we built all our instruments from protons and electrons. Something that only speaks to the exotic particles we create in accelerators. Theodore closes his eyes. Thinks about 50 years of physics education, of textbooks and lectures and equations on blackboards, all of it built on the foundation of 4 fundamental forces, all of it potentially obsolete. We need 5 sigma, he says, before we can claim this publicly. I know. CERN is upgrading the LHC. Run 3 starts next year, higher collision energy, better detectors, more data. Dominic pauses. If the anomaly is real, we will reach 5 sigma within a few years. And if it is not, then we will have spent billions of euros and decades of work chasing a statistical fluctuation. Dominic smiles grimly. But I do not think that is what is happening. Do you? Theodore thinks about the muon. That simple particle 200 times heavier than an electron living for 2 microseconds, precessing to a rhythm that physics cannot explain. He thinks about all the measurements, Brookhaven, Fermilab, CERN, Argentina, all pointing in the same direction, all whispering the same message. No, he says, I do not think it is a fluctuation. I think it is a signal. And I think, Dominic, that we are finally learning to hear it. They sit together in that cafe until the sun sets over the Alps, 2 old men staring at graphs on laptop screens, watching the universe refuse to obey, watching it oscillate. The summer of 2022 arrives with a question that physics cannot answer. 3 independent experiments, 3 different continents, 3 separate teams of scientists using different instruments, different methods, different particles, and all of them seeing the same thing, an anomaly. A deviation from the standard model, too persistent to be error, too consistent to be noise. A fingerprint left by something invisible, etched into the behavior of particles that live and die faster than a human heartbeat. Dr. Evelyn Thorne sits in her office at Fermilab, surrounded by monitors displaying cascades of data. She is 31 years old, hired 2 years ago as a data scientist. She has a background in machine learning, a PhD in computational physics, and a mind that operates in algorithms and neural networks. The coffee on her desk has gone cold again. Outside, the Illinois sun beats down on the prairie, but she does not notice. She is watching particles dance to a rhythm she does not understand. The algorithm she built took 6 months to develop. Neural networks trained on a decade of particle collision data, learning to recognize patterns that human eyes would miss. She taught it to filter out noise, to separate signal from background, to find needles in haystacks made of a billion pieces of hay. And it found something. Not just the anomaly Theodore measured. Something deeper. The muon precession is not constant. It fluctuates. Tiny variations, microsecond to microsecond, that average out to the anomalous value. But the fluctuations themselves are not random. They repeat. Every 230 microseconds, the pattern recurs. A rhythm, a heartbeat in the quantum noise. Evelyn runs the analysis 17 times, checking for instrumental artifacts, detector glitches, analysis bugs. The rhythm persists. She pulls up Dominic's beauty quark data from CERN, runs the same temporal analysis. The same rhythm appears. 230 microsecond period. Exactly the same. Evelyn picks up her phone. Her hands are shaking slightly from too much caffeine and too little sleep. She scrolls through her contacts, finds the number Dominic Archer gave her. The call connects after 3 rings. Dr. Thorne. His voice is clear despite the distance marked by that faint British formality. It is past midnight in Chicago. Should you not be sleeping? I found something, she says. In the data. A temporal pattern. A rhythm. It is in both datasets. Yours and ours. A pause. She hears the sound of papers being moved, a chair creaking. What kind of pattern? Periodic fluctuation. 230 microsecond period. The moon anomaly is not constant. It oscillates. And your beauty quark asymmetry does the same thing, synchronized. Another pause, longer this time. When Dominic speaks again, his voice is different, quieter. That is impossible. I know. The experiments are causally disconnected. There is no communication between them. No signal passing between Fermilab and CERN. I know, Evelyn repeats, but it is there. I have checked it 47 times. Run every control I can think of. The correlation exists. She hears typing, then silence, then a slow exhale. Send me your analysis. I want to verify it independently. Already sent. Check your email. More typing. Then a pause that stretches so long she thinks the connection has failed. Evelyn, Dominic says finally. His voice is barely above a whisper. You are right. The correlation is real. Weak, but statistically significant. When your muons exhibit excess precession, my beauty quarks decay preferentially to electrons. The correlation coefficient is 0.18. Evelyn leans back in her chair, staring at the ceiling tiles. What does it mean? How can particles on opposite sides of the planet be connected? I do not know, Dominic says. But if this is real, Evelyn, this is not just a fifth force. This is evidence of a field. A quantum field that permeates all of space, interacting with heavy particles simultaneously across any distance. A field. The word hangs in the air between them, separated by an ocean and a continent, but connected by a discovery that makes distance meaningless. In physics, forces are mediated by fields. The electromagnetic field carries photons. The gravitational field warps space-time. The strong and weak nuclear fields operate through gluons and W and Z bosons. If there is a fifth force, there must be a fifth field. And that field apparently has no respect for distance. Winter comes to Geneva with cold rain and gray skies. Inside the LHC tunnel, 500 feet below ground, engineers are making final preparations for Run 3. The superconducting magnets have been tested at full power. The cryogenic systems are stable. The detectors have been upgraded. Their electronics replace their trigger systems, reprogrammed. Dr. Henrik Volstad stands in the LHCb control room watching diagnostic screens scroll past status messages. He is 58 years old, built like someone who spent his youth working construction before discovering he had a gift for electronics. Norwegian by birth, American by choice, he came to CERN 20 years ago to help build the detector he now maintains. Henrik does not think of himself as a scientist. He is an engineer. He builds things, makes them work, keeps them running when they break, which is often. The theorists can worry about what the data means. His job is to make sure the data exists in the first place. But even an engineer can recognize when something extraordinary is happening. Dominic Archer walks into the control room carrying a tablet and looking tired. He has been working 18-hour day for months preparing for Run 3, analyzing old data, coordinating with Evelyn Thorne in Chicago. Henrik, he says by way of greeting. Status, all systems nominal. We are ready to take beam. And the trigger upgrade. Henrik pulls up a schematic on one of the monitors. Fully operational. The new trigger can handle 1 terabyte of data per second. No more hardware cuts. Everything is done in software now. We will record every collision, filter them in real time. Every collision, Dominic repeats. That is a lot of data. 40 million per second, Henrik confirms. The computing grid can handle it, barely. The real challenge will be analyzing it all. That is Dr. Thorne's problem. Dominic smiles faintly. She has been training neural networks to process the data stream. Apparently, machine learning is better at finding rare events than we are. Henrik nods. He has met Evelyn once via video conference. Young, brilliant, impossible to understand when she starts talking about algorithms. But her code works. That is what matters. When do we start? He asks. July 5th. First collisions at the new energy. The entire physics community will be watching. Dominic pauses. No pressure. Henrik laughs. I have been doing this for 20 years. Pressure is just another word for Tuesday. But he knows the stakes. They all do. If the muon anomaly and the beauty quark asymmetry are real, If the fifth force exists, then Run 3 is humanity's best chance to see it directly. To create the particle that mediates it, watch it decay, measure its properties. To prove that the whispers from the dark are not imagination. July 5th, 2022. The first proton beams of Run 3 circulate through the LHC at 6:47 a.m. Geneva time. 16 miles away, Theodore Blackwell watches the live stream from a hotel room still jet-lagged from the flight. In Chicago, Evelyn Thorne stands in the Fermilab control room monitoring the feed on a large screen. The beams stabilize, energy ramps up, 13.6 tera-electron volts per beam, higher than the LHC has ever achieved. At 8:23 a.m., the beams collide. Data floods into the detectors. Atlas, CMS LHCb Alice, all of them recording simultaneously their electronics processing particles that spray outward from the collision points. In the LHCb control room, Henrik watches the trigger system process events in real time. 40 million collisions per second, each one analyzed, categorized, filtered. The ones that look interesting are saved. The rest are discarded. Dominic stands beside him, a tablet in hand, monitoring the data quality. Luminosity is stable. Detector response nominal. We are in business. Henrik allows himself a small smile. No explosions yet. I call that a success. The first day of Run 3 produces 50 billion collisions. The computing grid processes them overnight, sorting events into categories: muon pairs, electron pairs, beauty quarks, tau leptons. The full menagerie of the standard model created and destroyed in fractions of a second, but no Z prime, no leptoquark, nothing that should not be there. It is too early, Dominic tells the team that evening. We need months of data, years probably. If the fifth force particle is as heavy as we think it will be, incredibly rare, 1 in a billion collisions, maybe fewer. How will we know when we find it? One of the graduate students asks. Dominic pulls up a simulation on the projector. If a Z prime is created, it will decay almost immediately, probably into a muon and an anti-muon pair, but the muons will be carrying enormous energy, far more than typical muon pairs, and the invariant mass will be wrong for any standard model process. So we look for high-energy muon pairs with anomalous kinematics. Exactly. Evelyn's neural network is trained to recognize that signature. If it exists, the algorithm will find it. If it exists, the run continues. Days become weeks. Weeks become months. The data accumulates. Trillions of collisions, petabytes of information. The neural network processes it all, searching for the pattern that should not exist, and finds nothing. By December, the statistical significance of the beauty quark asymmetry has climbed to 3.4 sigma. Better, but not enough. The Muon G2 anomaly remains at 4.2 sigma, tantalizingly close to discovery, but not quite there. Evelyn's temporal correlation persists. Verified now by 3 independent groups. Real, unexplained. But without direct observation of the particle itself, the community remains skeptical. Anomalies come and go. Statistical fluctuations masquerade as discoveries. The history of physics is littered with 3 sigma effects that vanished when more data arrived. The crisis comes in February of 2023, a contamination event. Something in the cryogenic system fails, allowing a microscopic amount of warm helium to enter the beam pipe. The LHC shuts down automatically, protecting the superconducting magnets. The repair takes 3 weeks. 3 weeks of no data. 3 weeks of lost collision statistics. 3 weeks closer to the end of Run 3 with nothing to show for it. Henrik Volstad does not sleep during the repair. He and his team work around the clock, replacing seals, testing systems, verifying that every component is ready. The pressure is enormous. Every day of downtime is a day of lost data. A day further from 5 sigma. When the LHC finally restarts, the relief is palpable, but the lost time stings. "We needed those collisions," Evelyn says during a video call with Dominic. Dark circles under her eyes. She has been running simulations calculating how much data they need to reach discovery significance. "I know," Dominic says, "but we are back online now. We just need to be patient." "Patient," Evelyn repeats. "We have been patient for 20 years, and we will be patient for 20 more if necessary." His voice is firm. "This is not a race, Evelyn. This is science. We do not publish until we are certain." But privately, he worries. The community is growing skeptical. Papers have been published questioning the muon G2 measurements, suggesting that the theoretical prediction might be wrong instead of the experiment. Other groups have failed to confirm the beauty quark asymmetry at the same significance level. The anomaly is not going away, but it is not growing stronger either. They are stuck, trapped between 3 sigma and 5 sigma in the purgatory of suggestive but not conclusive evidence. September 2023 brings an unexpected breakthrough. It does not come from CERN or Fermilab. It comes from the Pierre Auger Observatory in Argentina, a vast array of detectors spread across 500 square miles of pampas, watching for cosmic rays from space. Dr. Augustine Vale has spent 40 years studying cosmic rays. He is 73, white-haired, with the deliberate movements of someone who has learned to conserve energy. He was Theodore's contemporary, a theorist, while Theodore was an experimentalist, and they have had a friendly rivalry for decades. Augustine built his career defending the Standard Model. When Theodore first reported the muon anomaly, Augustine published a paper arguing it was likely a systematic error. When Dominic found the beauty quark asymmetry, Augustine suggested the theoretical predictions needed revision. He is not a believer, but he is honest enough to change his mind when the data demands it. The Auger Observatory has been collecting data for 15 years, measuring ultra-high energy cosmic rays that strike Earth's atmosphere. When these rays hit nitrogen or oxygen, they create showers of secondary particles, including muons. Augustine has been analyzing those muons, looking for the same anomalous behavior that Theodore measured, the same asymmetry that Dominic found, and he found it. The cosmic ray muons show the same excess magnetic moment, same preference for producing electrons over muons in their decays, same 230 microsecond rhythm that Evelyn discovered. 3 independent sources, now verified by a 4th team using completely different methods. Augustine publishes his results in October. The paper is careful, hedged with caveats acknowledging uncertainty. But the conclusion is unavoidable. The pattern is real. Theodore receives a phone call late at night, Augustine's voice sounding older than Theodore remembers. "Theo, I owe you an apology." "For what?" "For doubting you. For 20 years. A pause. "You were right. The muon anomaly is real. I see it in my own data now." Theodore sits up in bed, suddenly fully awake. "You found it. In the cosmic rays." "Yes, same signature, same statistical significance. I tried every systematic check I could think of. It does not go away." Another pause. "Theo, I have spent my career defending the Standard Model, teaching it, writing textbooks about it. And now you are helping to replace it." Theodore finishes gently. "Welcome to the club, Augustine. It is a strange feeling, is it not? Terrifying." Augustine admits, "I am 73 years old. Everything I thought I knew is potentially incomplete. Not incomplete about nothing, incomplete about the dark." Theodore pauses. Augustine in 1930, Wolfgang Pauli predicted the neutrino, a particle that barely interacts with matter. Everyone thought he was insane. But he was right. And when we finally detected neutrinos, it opened up an entirely new way of seeing the universe. Your point. My point is that being incomplete about the universe is not a failure. It is an opportunity. We get to see deeper, further, into places no one has looked before. Theodore pauses. "You are 73. I am 83. We may not live to see the full implications of this discovery, but we get to be the ones who open the door. That is not a bad legacy. Silence on the line. Then softly, no, I suppose it is not. They talk for another hour. Two old men, both having spent lifetimes in physics, both watching the paradigm shift beneath their feet. The year 2024 passes in a blur of data and analysis. The LHC runs continuously except for brief maintenance periods, billions of collisions per week. The datasets grow so large that even with the world's most powerful computing grids, the analysis cannot keep up. Events are processed, categorized, archived for future study. Evelyn's neural network evolves. She trains it on more data, refines its pattern. Recognition teaches it to look for ever more subtle signals. The algorithm becomes better at its job than she is, better than any human could be. In June, it flags an event. Beauty quark creation and decay. But the decay products are unusual. Two muons carrying combined energy of 3.2 tera-electron volts. The invariant mass suggests they came from a parent particle with mass around 3.2 TeV. 3.2 TeV. Exactly where theory predicts the Z prime should be. Evelyn stares at the event display for an hour. It could be the Z prime, or it could be a statistical fluctuation. One event proves nothing. She needs more. The algorithm continues searching. July passes. August, September. 47 more candidate events appear, all with similar characteristics. High-energy muon pairs. Invariant mass clustering around 3.2 tera-electron volts. But 47 events is not enough. Not for a 5 sigma discovery. They need hundreds, thousands. The data accumulates slowly, too slowly. By December, they have 89 candidate events. The statistical significance is climbing, 2.1 sigma. Better than nothing. Not good enough. Dominic runs projection calculations. At the current rate, they will reach 5 sigma in late 2025, just before Run 3 ends, if they are lucky, if the LHC does not have another failure, if the signal is real and not a mirage. January 2025. Theodore Blackwell celebrates his 86th birthday alone in his house outside Chicago. His daughter calls from California. His son sends a card. Old colleagues send emails. He makes himself dinner, soup and bread, sits at his kitchen table looking out at snow falling on the prairie. He thinks about the muon, that simple particle he has been chasing for a quarter century, precessing its way through magnetic fields, refusing to obey the equations. His phone buzzes. A text from Evelyn. Statistical significance at 2.9 sigma, climbing steadily. We are going to make it. Theodore types back slowly, his fingers stiff with age. How long? 10 months, maybe 11. By Christmas. Christmas. He will be 86 years and 8 months old by then, if he is still alive, if his health holds, if he makes it long enough to see the confirmation he has been waiting for since 2001. He looks at the snow, thinks about patience, about spending your life working toward an answer you might not live to see. Science is not kind to human timelines, but it is honest. Eventually. Theodore finishes his soup, goes to his desk, opens his laptop, starts writing an email to Dominic and Evelyn and Augustine and Henrik. We are close, he types. After 24 years, we are finally close. Do not lose faith now. The universe is patient. We must be patient too. He hits send, closes the laptop, goes to bed early. Dreams of muons, processing in perfect formation, dancing to a rhythm from the dark. The spring and summer of 2025. pass in anxious incrementation. 3 sigma in March, 3.5 in May, 4 sigma in July. The candidate events accumulate: 147, 203, 312. Each one is scrutinized, background processes are estimated and subtracted, systematic uncertainties are evaluated, control samples are analyzed to verify the detector is working correctly. The signal persists. By September, they have 423 candidate events. The invariant mass distribution shows a clear peak at 3.21 tera-electron volts. The Z prime. It has to be. The statistical significance reaches 4.7 sigma. So close. We need 2 more months, Evelyn says during a collaboration meeting. Maybe 3. The projection shows we will reach 5 sigma by late November. The run ends in December, someone points out. I know. Tension fills the room. They are so close, but close is not enough. Physics demands 5 sigma. Anything less is suggestive, not conclusive. What if we do not make it? A graduate student asks. What if we end the run at 4.9 sigma? Silence. Dominic speaks up. Then we petition for an extension, or we wait for the next run, or we build a better collider. His voice is steady, but we do not publish a discovery claim until we have 5 sigma. Period. The meeting continues. Systematic uncertainties are discussed. Background estimates are revised. The collaboration prepares for the final push. Henrik Volstad monitors the LHC status day and night. No failures, no contamination events. The machine runs flawlessly as if it knows what is at stake. November arrives cold and clear. 4.8 sigma, 4.9 sigma. Theodore Blackwell flies to Geneva on December 10th. He is not sure he should be traveling at his age, but this is too important to miss. Evelyn arrives the same day. Augustine comes from Argentina. They gather in the CERN cafeteria 4 physicists spanning 2 generations waiting for the final data to be processed. How long? Theodore asks. Hours, Dominic says. The last week of collisions is being analyzed now. If the trend continues, we should cross 5 sigma tonight. Tonight, after 24 years. They sit together drinking coffee that has gone cold, watching the winter sun set over the Alps, waiting for the universe to speak. December 24th, 2025, Christmas Eve. The LHCb control room is nearly empty. Most of the collaboration has gone home for the holidays, families waiting, children expecting presents. The normal rhythms of life continuing while deep underground protons circle at the speed of light. Dominic Archer sits at a workstation watching data stream across monitors. Henrik Volstad is 3 consoles over monitoring detector systems. Evelyn Thorne connects via video link from Chicago, her face pale in the glow of her screen. Theodore Blackwell sits in a chair near the back of the room oxygen tank beside him. His breathing is labored. The flight to Geneva exhausted him more than he wants to admit, but he refused to stay in the hotel. Not tonight. Not when they are this close. The clock reads 11:34 p.m. Statistical significance at 4.98 sigma, Evelyn reports. Her voice is steady, but Theodore can hear the tension underneath. We need approximately 100 more candidate events to cross the threshold. Beam conditions are stable, Henrik says. Collision rate nominal. We are producing events as fast as the detector can record them. Dominic pulls up a projection graph. At current rate, we should reach 5 sigma in approximately 40 minutes. 40 minutes. Theodore closes his eyes, thinks about 2001, about seeing that first anomaly and knowing somewhere deep in his bones that it was real. About 24 years of checking and rechecking, of colleagues who thought he was chasing shadows, of nights lying awake wondering if he was wrong, 40 minutes to vindication, or 40 minutes to nothing. The room falls into silence, broken only by the hum of electronics and the soft click of keyboards. On the monitors, event displays flash past. Particles created and destroyed in microseconds, their trajectories traced by detector elements, their energies measured with impossible precision. Most are ordinary, expected. The standard model playing out exactly as predicted. But some are different. 11:47 p.m. Evelyn's neural network flags an event, then another, then 3 more in rapid succession. Something is happening, she says. Her voice has changed, higher, urgent. I am seeing a cluster, multiple candidate events within seconds of each other. Dominic pulls up the event displays. 5 beauty quark decays, all producing high-energy muon pairs, all with invariant masses consistent with a 3.2 TeV parent particle, then 10 more, then 20. This is not normal, Henrik says. He is checking detector diagnostics looking for malfunctions. The collision rate has not changed, but we are seeing an order of magnitude increase in candidate events. Evelyn is typing frantically. Numbers scroll across her screen. It is not a detector issue. The events are real. They are just all happening at once. Theodore struggles to his feet, crosses to look at the monitors. His heart is pounding in a way that worries him, but he ignores it. How many? He asks. 47, Evelyn says. No, wait. 63. Still climbing. The neural network continues flagging events. The counter increments. 79, 92, 106. This is impossible, Dominic whispers. We have been running for months and averaging 3 or 4 candidate events per day. Now we are seeing dozens per minute. Statistical fluctuation, Henrik suggests, but his voice lacks conviction. Not at this magnitude. Evelyn pulls up a probability calculation. The odds of this being random are less than 1 in 10 billion. 127 candidate events. Then the cascade stops. Silence in the control room. Everyone staring at screens trying to process what just happened. Total time span of the cluster, Evelyn says slowly, was 4.3 seconds. 4.3 seconds in which the universe decided to cooperate, in which Z-prime bosons materialized from the quantum vacuum in unprecedented numbers, in which the fifth force hiding for billions of years suddenly shouted instead of whispered. Dominic runs the calculation. His hands are shaking. With the new events, total statistical significance is... He stops, stares at the number. 5.2 sigma. The words hang in the air. 5.2, not 4.9. Not the marginal crossing they expected, but a clean, undeniable, overwhelming confirmation. Theodore sits down heavily. His breathing is ragged. Henrik moves toward him concerned, but Theodore waves him off. I am fine, he says. But tears are running down his weathered face. I am fine. I needed to see this. Evelyn is checking the data from every angle, running control analyses, verifying detector calibration, looking for any possible error. It is real, she says finally. The cluster is real. The events are real. 5.2 sigma is real. Dominic stands up, walks to the window overlooking the detector. The massive machine sits in its cavern surrounded by scaffolding and cables illuminated by harsh fluorescent lights. We did it, he says quietly. After 24 years, we actually did it. Henrik is already checking the event kinematics. The invariant mass peak is at 3.21 TeV with an uncertainty of 0.04. The decay signature is exactly what we predicted for a Z-prime boson coupling preferentially to heavy leptons. The fifth force, Theodore says. His voice is barely above a whisper. The fifth fundamental force. Real. Confirmed. 5 sigma. Evelyn pulls up a timeline on her screen. April 7th, 2001. Theodore sees first muon anomaly at 2.6 sigma. March 2019. Dominic confirms beauty quark asymmetry at 3.1 sigma. April 2021. Fermilab confirms muon anomaly at 4.2 sigma. December 24, 2025, 11:47 p.m. Fifth force confirmed at 5.2 sigma. She pauses. It is Christmas Eve. Dominic laughs. A single sharp bark of sound. Of course it is. The universe has a sense of timing. Theodore stands again more carefully this time, crosses to where Dominic is standing. The two men separated by 24 years of age, united by 2 decades of searching. You were right, Dominic says. In 2001, when everyone doubted. You were right. We were right, Theodore corrects. All of us. You, Evelyn, Augustine, Henrik. Everyone who refused to stop looking. He turns to face the detector. The muon tried to tell us. 24 years ago, it precessed wrong and we finally learned to listen. The announcement comes on December 26th. CERN releases a press statement, carefully worded, hedged with appropriate scientific caution, but the conclusion is unavoidable. Analysis of data from LHC Run 3 has revealed a new particle with mass approximately 3.21 tera-electron-volts decaying to muon pairs with statistical significance exceeding 5 sigma. The particle's properties are consistent with theoretical predictions for a Z-prime boson mediating a previously unknown fundamental force. The physics community erupts. Email servers crash from the volume of messages. Conference calls are hastily organized. Theorists dust off decades-old papers predicting Z-prime bosons and leptoquarks. The media picks up the story more slowly. Science journalists struggle to explain what it means. Headlines range from sober, new fundamental force discovered at CERN, to breathless, scientists find hidden dimension of reality. Theodore watches the coverage from his hotel room. Augustine has flown in from Argentina. They sit together, two old men who spent their careers on opposite sides of a debate that has finally been settled. I owe you more than an apology, Augustine says. You were right for 24 years while I was wrong. You were not wrong, Theodore says. You were appropriately skeptical. That is what science requires. But I delayed acceptance, made it harder for funding agencies to support the work. Theodore shakes his head. Skepticism is the price of rigor. If every 3 sigma anomaly was treated as gospel, physics would be chaos. He pauses. Besides, you changed your mind when the data demanded it. That is all anyone can ask. They watch a news broadcast together. A physicist from Stanford is being interviewed explaining what the fifth force means. The Standard Model described 4 fundamental forces governing all interactions in the visible universe, the physicist says. But the visible universe is only about 5% of the total mass energy content. The other 95% dark matter and dark energy has been a complete mystery. This discovery suggests there may be an entire dark sector with its own forces, its own particles, its own physics. And the Z-prime boson is our first glimpse into that hidden realm. They make it sound simple, Augustine says. It is simple, Theodore replies. Explaining it is hard. January 2026. The collaboration publishes their results. The paper is 53 pages long with 247 authors. It details the detection of the Z-prime boson, its mass decay modes, and coupling strengths. The statistical significance is listed as 5.2 sigma. The certainty threshold has been crossed. Peer review is swift. The data is solid. The analysis is rigorous. Within 2 weeks, the paper is accepted by physical review letters. Theodore is listed as an honorary author, though he contributed no direct analysis. The collaboration insisted. Without his initial measurement in 2001, none of this would have happened. He receives congratulatory emails from around the world, old students, former colleagues, people he has not heard from in decades. The Nobel Committee releases a statement. The discovery is too recent for this year's prize, but speculation begins about 2027 or 28. Theodore knows he will not live that long. His doctors have told him as much. Heart failure slowly progressing, months, maybe a year, but he has seen the discovery confirmed. That is enough. February brings a different kind of recognition. The Dark Signal Institute is announced, a collaborative effort funded by the European Union, the U.S. National Science Foundation, and private donors. $2 billion over 10 years. The mission map, the dark sector. Dominic is named Director of Experimental Physics. Evelyn becomes Director of Data Science. Augustine, despite his age, accepts the position of Senior Theoretical Advisor. Henrik Volstad is appointed Director of Engineering, tasked with designing the next generation of detectors. The Institute's headquarters will be at CERN, but it will coordinate research worldwide. New particle accelerators are proposed. Dark photon telescopes, gravitational wave detectors sensitive to dark matter interactions. The goal is not just to study the Z-prime. It is to explore the entire dark universe that the fifth force has revealed. Theodore attends the announcement ceremony. He sits in a wheelchair, now oxygen flowing through a nasal cannula. But his mind is clear. When Dominic gives his speech, he mentions Theodore by name. 24 years ago, Dr. Theodore Blackwell saw something that should not exist. A muon precessing wrong. He could have ignored it, blamed it on error, moved on to easier questions. Instead, he spent the rest of his career proving it was real. This institute exists because one scientist refused to stop asking why. The audience applauds. Theodore raises a hand in acknowledgement, embarrassed by the attention. March 15th, 2026. Theodore Blackwell dies peacefully in his sleep at the age of 86. His funeral is attended by hundreds. Physicists from around the world. Students he taught decades ago, colleagues who worked beside him. Dominic gives the eulogy. Theodore once told me that the most important things are invisible. Love, hope, the forces holding the universe together. He spent his life studying the invisible, and in doing so, he revealed a hidden dimension of reality that will occupy human inquiry for centuries to come. He pauses, looks at the casket. The muon precesses Theodore. It precesses because the universe is richer than we knew. Thank you for showing us how to listen. The casket is lowered into frozen Illinois ground. Snow falls softly. That evening at CERN, the LHC begins its next run. The detectors activate. Protons accelerate. The search for the dark universe continues. 1 year later, February 2027. Evelyn Thorne stands in the new Dark Sector Observatory, a facility built specifically to detect dark photons. The detector is a marvel of engineering, superconducting cavities tuned to resonate at frequencies predicted by theory, cooled to microkelvin temperatures, shielded from cosmic rays and electromagnetic interference. If dark photons exist, the carriers of dark electromagnetic force, this machine should be able to detect them. The first test begins at midnight Geneva time. Henrik has spent 18 months building the apparatus. Every component checked and rechecked. Every potential source of noise eliminated. Dominic watches from the control room. Augustine is there too, now 75 still sharp. The detector activates. For 3 hours, nothing. Then, at 3:17 a.m. a signal. Faint, barely above background. But there. A resonance at exactly the frequency predicted for dark photons coupling to the Z-prime field. Did we just... Henrik stops. Starts again. Did we just detect dark light? Evelyn runs the analysis. Cross-checks against control data. Estimates background. Preliminary significance is 2.1 sigma, she says. Not enough to confirm, but enough to keep looking. They run for a week. The signal strengthens. 3.4 sigma. 2 months later, 4.6 sigma. By summer, 5.1 sigma. The dark photon exists. The fifth force is not alone. The discoveries cascade. 2028 evidence of dark atoms. Structures in the dark matter distribution that suggest binding by dark electromagnetic forces. 2029. A second heavy boson is found. Not Z prime, but something else. Possibly a dark version of the W boson. 2030 gravitational wave detectors pick up anomalous signals. Possibly dark matter objects colliding, held together by dark forces. The dark sector is not empty. It is full. Full of forces and particles and structures that have been invisible to us for the entire history of human civilization. We have been living in a universe twice as complex as we thought, and we are only beginning to understand it. December 24th, 2030, 5 years after the Christmas Eve discovery. Dominic Archer stands in the LHCb control room, now upgraded with new detectors sensitive to an even wider range of particles. He is 73 years old. Thinking about retirement, but not yet. Henrik is there. Evelyn connects via video from Chicago. Augustine joins from his home in Argentina, his video feed showing white hair and a weathered face. They have made this pilgrimage every Christmas Eve since 2025. A tradition, a remembrance. To Theodore, Dominic says, raising a coffee cup. To Theodore, the others echo. They sit in companionable silence, watching data stream across monitors. The LHC is running. It never stops during the holidays anymore. Too much to discover. Do you think he knew, Evelyn asks, how big this would become? Dominic considers. I think he knew it was important, but I do not think any of us understood the scale. We thought we were finding one new force. Instead, we found an entire parallel physics. Parallel universe, Augustine corrects. Not separate. Overlapping. Interacting. Connected through the fifth force. And whatever others we have not found yet, Henrik adds. The monitors flash. Another Z prime event. They barely notice now. The anomaly has become routine. The impossible has become data. Strange to think, Evelyn says that 5 years ago we did not know any of this existed. The dark photon, the dark atoms, all of it hidden. Not hidden, Dominic says, just invisible to us. We were asking the wrong questions, looking in the wrong places. He smiles. Theodore taught us to look where the standard model said nothing should be, and we found everything. The year is 2050. A new particle accelerator has been built. The Very Large Hadron Collider, circling beneath 3 countries, 100 kilometers in circumference, capable of reaching energies of 100 tera-electron-volts. Dr. Maya Hartwell stands in the control room. She is 24 years old, the youngest PhD in the VLHC program. She wears a small pin on her lab coat, a stylized muon spinning. Her grandmother gave it to her before she died. Your great-grandfather wore this, she had said. Theodore Blackwell. He discovered the fifth force. Maya never met Theodore. He died 18 years before she was born. But she knows his story. The muon that precessed wrong. The 24 years of patience. The Christmas Eve miracle. She chose physics because of that story. Because she wanted to continue the search her great-grandfather started. The first collisions at the VLHC are scheduled for today. The entire physics community is watching. Maya thinks about Theodore. About a man who saw a muon precess wrong and refused to let it go. Who spent 24 years being right while the world was skeptical. The beams circulate. Energy ramps up. 100 tera-electron-volts per beam. At 3:47 p.m. Geneva time, they collide. The detectors light up. Data floods in. And within the first hour, they see it. Not a Z prime, something heavier. Mass around 15 tera-electron-volts. A new particle, coupling to dark matter directly. Statistical significance already at 4 sigma and climbing. Maya watches the event displays. Theodore's photograph looks back at her from her phone screen, old, weathered, smiling slightly. She picks up the phone. "We are still listening, Great-Grandpa," she whispers. "The universe is still talking, and we are still learning its language." The detector chimes. Another candidate event, then 3 more. The dark sector revealing itself layer by layer, secret by secret. The search continues. It will always continue. Because once you learn that reality is deeper than you thought, you cannot stop digging. Once you hear the whisper from the dark, you cannot unhear it. The muon precesses, the universe speaks. And somewhere in the quantum foam that underlies all existence, the fifth force vibrates, patient, eternal, waiting for the next generation to ask the next question, waiting for human curiosity to reach deeper into the dark. The invisible ocean is vast, but we have learned to swim, and we are not alone in the water.